One of the simplest types of functions that we can have is a line. And for a line, we can have the slope of the line telling us the direction the line is going. But we would like to go further than only looking at directions of lines, but really also talk about what direction is a function going, even if that function happens to be curved. And so, for instance, here is a picture, a graph of a curved function. It certainly is not a line, it's nowhere a line, but we can still look at x values. Let's call that particular x value c there. We can find a point there where the x value, input value, is c, and that y value that goes with it, the output value, is f of c. Now we have a sense, as we're always moving from the left to the right, that this function is kind of going up. And we see also, if we take that point c comma f of c on the graph of the function and draw a tangent line to that function, then we have that upward sloped line there. And so here for this one, we're looking at a tangent line. Okay. So we have a tangent line. We have a curve that's f of x there, and we have a point on the curve, and we've drawn a tangent line to it. And we're going to introduce this notation here. The slope of this tangent line is this, f prime of c. Now that new notation is standing for the derivative. So the derivative, that's our new term there, of f of x at x equals c. Okay? So, great, we've got this line. We know whatever its slope happens to be is going to be the derivative. But the problem here is, for a tangent line, we only have one point. But in general, we have a slope formula here from algebra, and that slope formula starts with 2 points. So let's call these points x1, y1, and x2, y2. Anytime we have 2 points, we can find the slope of the line that goes through those 2 points using this formula here. It's change in y over change in x. So we'll say y2 minus y1, and then in the denominator it would be x2 minus x1. Of course, the order of the points doesn't matter as long as they're consistent in the subtraction. So that's our slope formula from algebra. It requires 2 points, but here in calculus, we want to be able to find the slopes of lines where we only have 1 point that we're really holding on to. That c comma f of c is the single point on our function that's also on our tangent line. So we need a way to be able to utilize the slope formula to give us some information about the slope of this tangent line. And what we do then is we're going to be looking at secant lines instead. Okay. So just like we had a tangent line over here and we looked at the graph, let's take a look at this secant line. Certainly we're going to still have that point c comma f of c that we care about ultimately. But what we're going to do is, instead of looking at that single point, we're going to go slightly away from that point for a new x value. Let's call that new x value z. Z is going to be c plus a little bit. That little bit is defined to be h here for our notation. So we've got this second x value, which gives us a second output value here also, f of, we'll say c plus h. There. And now we have 2 points that are on the function, and if we were to draw a line that connects those 2 points, we would see, we could assess what the slope of that line is. So now let's take a look at what the slope of the line is. So remember, the 2 points that we have here are c, f of c, that's 1 point, and the second point that we have is, we could call it z, f of z, or we could also call it the c plus h. That's what we were calling z, and then the output value would just be if we plug that c plus h into our function. Okay, so those are our two points. And we can do this, we can use the slope formula that we have to figure out, or with these, I guess with the 2 points, the notation that we're using within the 2 points. So here we would have the slope then be, let's see, we'll do the c plus h first. So our change in y would be our function values, our output values. So it would be f of c plus h minus f of c, okay, over the input values are the c plus h and then the c. So I'm subtracting those in the same order then. But take a look at what you have here in the bottom. The bottom is c plus h minus c. And sure, we have the parentheses there, but they actually can be dropped. So the c minus c cancels, leaving you simply with h in the bottom. And then your top, you've got this f of c plus h minus f of c. Okay. The other thing that we could get out of this whole setup, if we were using the z's instead, is we could have f of z minus f of c over z minus c. So each one of these is really just the slope formula for 2 different points, the cf of c and then that secondary point that gave us a secant line. But each one of these we call a difference quotient. And the idea is we're going to be able to approximate the tangent line, the slope of the tangent line, by looking at the slopes of the secant lines where we're going to let that h go to 0, or we could think about it equivalently as saying the z approaching c. So some terminology that goes along with this. Basically, our new thing that we have is this derivative function, f prime. It's the derivative of the original function f. And we know that to handle this derivative, we need to approximate f prime with something also. So what we've done so far is this derivative we're equating with the slope of the tangent line. So that derivative is the slope of the tangent line that we are approximating with the slope of the secant line. So that's what we did in the development of these ideas. The other thing that you want to, what you'll hear about in some sort of application type problems would be something called instantaneous rate of change. So the rate of change is going to be the slope of these particular lines we care about, but the terminology instantaneous rate of change is dealing with the single point, just like the tangent line had the single point. In comparison, instead of instantaneous rate of change, we'd be talking about average rate of change. For the terminology that would go with the approximation. A few other things that we could hear that would go along with the f prime, the derivative function, could be, you could just hear it simply as the slope function. Because what happens is, for whatever x value we have that's in the domain of the function, we could perhaps, unless there's kind of a strange point that's happening, talk about what the slope of the tangent line would be at that point. So in some sense, the f prime function is outputting the slopes of those tangent lines. So we could kind of think about it as our slope function. The other thing that may come up in some application type problems is f prime is actually velocity whenever we have f being the position of a function. So I'll put that in there. When f is position. So these are the sorts of things you may read, and you need to be able to equate, especially here with the derivative. The derivative you could equate with the slope of the tangent line, instantaneous rate of change, in general the slope function, or perhaps even velocity. A couple more observations to go along with this in the introduction here would be for these sorts of problems, for these sorts of functions, anytime we can draw a nice tangent line, we can say that that derivative exists. So like over here, this is about where our C was in the initial one, but what we see here is that f prime is positive because the slope of the tangent line is positive, and notice that f is going up. Okay. In comparison, if we were to pick a point over here on the other side and draw the tangent line, notice here that f prime is going to be negative because the slope of that tangent line is negative, and we also have that f is going down. So that direction of the tangent line is really giving you the direction of the graph. And in particular here at this nice smooth peak top point there, right in there, we've got that f prime is equal to 0. And that's in kind of the maximum point there of our nice smooth graph. Now looking at this second graph, the one interesting place that we have is this corner point here. That corner point actually has no tangent line. And notice here that the function is not smooth. Okay, it's not smooth there at that one point. The direction changes abruptly. To the left, we're going down. To the right, we're going up. But there, right there at that corner point where we're changing directions, it doesn't happen smoothly at all. We don't have a well-defined tangent line there. And so what we're going to find out there is that the derivative actually doesn't exist at that corner point there.